All right, welcome back, everyone. I am seriously thrilled to have you here for this explainer covering Chapter 5 of the Ultimate C Programming Handbook. So today we are taking a massive leap forward. If you've been following along, you've totally got the basics of writing code down. But today is all about the architecture. We're going to learn how to structure our code like professional software engineers using functions and recursion. Trust me on this one. By the end of our time today, the way you look at a blank screen of code is going to completely change. Let's get right into it.
Here's our roadmap for today's explainer. Number 1, recap, looping back. 2, introduction to C functions. 3, anatomy of a function. 4, passing values in C. And finally, number 5, the magic of recursion.
Okay, first up, Section 1, recap, looping back. Let's take a quick look in the rearview mirror.
In our last explainer for Chapter 4, we tackled this huge core concept of loops. And, why do we even need them? Well, honestly, because as programmers, we hate manual labor. If we need to execute a set of instructions over and over again, writing that same code out manually is just exhausting, and frankly, it's a great way to introduce typos and errors. So we use loops to automate that repetition. We looked at 3 main tools for this. First, the while loop, which is kind of like a bouncer at a club, right? It keeps its block of code running as long as a specific condition stays true. Then we saw the do while loop, which is a bit unique because it guarantees the code runs at least one single time before it even bothers to check the condition. And finally, the for loop, which we love because it neatly packages our initialization, our test condition, and our increment counter all into one incredibly efficient line of code. Using these loops is great for repeating instructions in one specific spot in our program, but as you're going to see, when our programs start getting bigger and more complex, a really interesting problem pops up.
Which brings us to Section 2, Introduction to C Functions, Code Reuse Made Easy.
Think about this for a second. Loops are absolutely fantastic if you want to, say, print the word hello 10 times in a row right then and there. But what if your program is bigger? What if you need to print a really specific, customized user menu at the very beginning of your program, and then you need that exact same menu in the middle, and then again at the very end? If you just copy and paste that chunk of code every single time you need it, your program is going to become this massive, messy, impossible-to-read document. In the programming world, we actually call that spaghetti code. It's just a tangled mess. We clearly need a better way to reuse code across completely different parts of our program without just copy and pasting.
And the brilliant solution to that problem is a function. Basically, a function is just a block of code that is designed to perform one particular task. You write it once, you give it a name, and then you can reuse it any number of times from anywhere in your entire program, literally just by calling out its name. Think of it like delegating a task to an assistant. Instead of you, the main program, doing all the math or all the printing yourself, you hand it off to this highly specialized assistant, the function, who goes off, does it for you, and hands you back the result. It keeps everything super clean, it tracks exactly what is happening where, and it lets you test little pieces of your logic entirely on their own.
Now, you actually have 2 flavors of functions at your disposal in C. The first are called library functions. These are built right into the C language for you. They're basically prepackaged solutions for common tasks, grouped together in library files on your computer. For example, printf. We've used it dozens of times already. You didn't have to write the incredibly complex, low-level code to make pixels light up on your monitor, right? The creators of C already did that. You just used their library function. The second flavor is user-defined functions. These are the custom tools that are declared and defined entirely by you, the programmer, to solve whatever specific problem you're working on.
So, how do we build one? Let's move to Section 3, Anatomy of a Function.
Building your own custom function might seem a little intimidating at first, but it literally just breaks down into 3 simple logical steps. Step 1 is the function prototype. Step 2 is the function call, and Step 3 is the function definition. And just a heads up, if you miss any of these 3 pieces, the C compiler is going to throw a big error at you. Let's look at exactly what each of these means in actual code.
Okay, let's walk through this syntax line by line. Right up at the top, outside of our main program block, we have void display semicolon. This right here is the function prototype. Think of it kind of like handing the compiler a business card. It's just telling the computer, hey, just so you know, a function named display exists. It doesn't take any inputs, and that void keyword just means it doesn't return any answers back to you. I'm going to actually define it later. Next, look inside the int main block. See where it says display? That is the function call. This is you telling the program, okay, pause what you're doing here in main, jump over to that display function, run it, and then come back when you're done. And finally, down at the bottom, we have the function definition. void display, parentheses, printf hi, IAMDisplay, semicolon. This is the meat and potatoes. This is where the actual work happens. The program executes whatever instructions are inside those curly braces. Once it finishes printing that message, it zips right back up to the main function and just picks up right where it left off.
All right, section 4, passing values in C. How do we get raw data into these functions?
To pass values in and out of our functions, we really need to clear up a classic beginner stumbling block, the difference between parameters and arguments. When you are first defining your function, like writing out the recipe, you use parameters. These are simply empty variable placeholders. For instance, if you write a definition like int sum int a, int b, those letters, a and b, they're just empty boxes waiting for data. On the flip side, arguments are the actual concrete values that you pass into those boxes when you finally make the function call in your main program. So if you type sum, 2, 3, the numbers 2 and 3, those are your arguments. Arguments are the things that go into the parameter boxes. Make sense?
Now, this right here illustrates one of the absolutely most critical rules in C programming. It's called call by value. Let's look at this little narrative in the table. In our main program, we declare int b equals 22. Pretty standard. Then we pass b as an argument to a function called change. Inside that function, the code tries to say b equals 77. So you might logically think, awesome, my variable is now 77. But look at the third step. When we go back to main and print b, it is still 22. Why? Well, because in C, we don't actually pass the original variable to the function. We literally only pass a copy of the value. The function can do whatever it wants to its own local copy, but your original variable in the main program remains completely untouched and perfectly safe.
This little sketch perfectly captures the essence of what we're talking about with call by value. Imagine you have a square, and you know the length of side A. You don't want to do the math to find the area yourself. So you don't give the function the actual square, you just pass a copy of that value A, maybe written on a sticky note, to a library function. You're basically asking, hey, here's a number, what's the area? The function takes that copied value, goes into its own little isolated room to do the math, and then simply hands you back the final answer. It doesn't permanently alter your original side A in any way. It just uses it as a raw input to generate an output.
Okay, brace yourselves. Section 5, the magic of recursion, a function calling itself.
The absolute core definition is right here. Recursion is simply a function that calls itself. And I know, that sounds like a total paradox. How can a function call itself while it's still running inside itself? It's wild. Think of it like standing between two mirrors and seeing an infinite reflection trailing off forever. Or, even better, think of those wooden Russian nesting dolls. You open the biggest doll, and inside is a slightly smaller identical doll. You open that one, and there's an even smaller one inside. In programming, some really complex problems are actually just a large problem made up of smaller identical subproblems. Let's trace this out with the absolute classic example of recursion, calculating a factorial. In math, 5 factorial means 5 times 4 times 3 times 2 times 1. But another way to say that, right, is that 5 factorial is simply 5 multiplied by 4 factorial. We've literally defined the problem in terms of itself. Follow the arrows down the slide with me. If we call our function factorial of 5, the function says, okay, easy, my answer is 5 multiplied by a factorial of 4. It pauses its own math and calls a new copy of itself, this time passing the number 4. That new version says, well, I'm 4 multiplied by a factorial of 3. And this just keeps stepping down, opening smaller and smaller nesting dolls until it finally hits factorial of 1. At that exact moment, it stops stepping down. The actual math finally gets calculated, and the answers bubble all the way back up the chain to hand you the final complete result.
But listen closely to this part because it is incredibly important. The condition in a recursive function that stops further recursion is called the base case. In our factorial example, hitting the number 1, that was our base case. If you write a recursive function and you forget to include a base case, or you write the logic for it incorrectly, the function will just keep calling itself forever. The mirrors will literally reflect infinitely. The computer will just keep opening nesting dolls until it completely runs out of memory, causing a massive program crash that we call a stack overflow. So pro tip, always establish your base case first when you're writing recursive code.
Wow. All right, we have covered some serious professional-level architectural ground today. Let's quickly recap. Functions are our way to chunk code together so we can reuse it cleanly and avoid that dreaded spaghetti code. To build one, you gotta have a prototype to announce it, a call to use it, and a definition to give it its actual instructions. We learned that we pass arguments into parameter placeholders, but remember, C only passes a copy of the value, which protects our original variables. And finally, we explored the mind-bending magic of recursion, where a function calls itself to solve nested problems. And what's the golden rule? Always include that base case.
You are well on your way to writing highly organized, structured C programs. But before we wrap up, I want to leave you with a bit of a puzzle to chew on. We talked a lot today about call by value. We learned that if a function tries to change a variable we pass to it, it only changes a copy. The original variable back in our main program stays exactly the same. But what if we want the function to change the original variable? What if we literally want to reach directly into the computer's memory and alter the data right at its source? How on earth do we bypass the copy system and do that? Well, that is a fantastic question, and the answer involves call by reference, using a wildly powerful tool called pointers. But hey, that is a story for Chapter 6. Thanks so much for learning with me on this explainer, and I'll see you in the next one.